Welcome back to the 9th video about the Melexis MLX90363 Triaxis Magnetometer. Last time we got so far that we were actually able to configure that thing while at the same time avoiding unnecessary EEPROM writes. Card here, link in the description. Now there are only 6 messages left to implement. 2 regarding a diagnostic and 4 regarding measuring an internal oscillator of our little chip. And that's exactly what we will implement today. Enjoy! So let's dive right in and start with the diagnostic stuff. So we have here a MOSI message, diagnostic details, that requests a diagnostic answer, MISO message from the slave. And yeah, I have given up about the names. They're again completely different all over the datasheet. Anyway, the opcode for the MOSI message is hexadecimal 16 and for the MISO message hexadecimal 17. The MOSI message is basically an empty message, so not much to implement there. Just create that opcode and one method that we can send that message to our slave. Please note it's called here diagnostics with an S details, like also here diagnostics in the heading. The MISO message is another kind of beast. It's called here diagnostics, diagnostic details. First, we have here 21 bits called diagnostic bits. Each bit, of course, indicating some error condition. We will see section 17 for that. Then we have here a 6-bit field anadiag-kunt. That stands for analog diagnostic or diagnostics counter. And then a 2-bit field FSMerc, which stands for, it's never really explained anywhere, fail safe mode error condition or something like that. Please note here, anadiag count is a sequence loop counter referring to the analog class diagnostics, all others, or whatever that means. That's the only explanation for this counter here. Let's have a look now at the meaning of that 2-bit FSMerc field. So it says here, parameter FSMerc reports the root cause of entry in failsafe mode. And if you rearrange the words, FSMerc could actually stand for failsafe mode entry root cause. So I was wrong the first time. So 0 means the chip is not in failsafe mode. 1 means built-in self-test error happened and the chip is in failsafe mode. 2 means digital diagnostic error happened and the chip is in failsafe mode. And 3, one of the 5 error interruptions listed above happened and the chip is in failsafe mode. We'll have a look at those in a second. Anyway, I've here written also down the bit patterns when we consider FSMerc as just the 2 most significant bits in this byte here. So, the error interruptions mentioned above. If FSMerc is equal to 3, our analog diagnostic counter takes another meaning. And here I spot a little problem. So we have here values between 193 and 199. However, our counter field is only 6 bits, so it can only have values between 2 to the power of 6 minus 1, that's 63, and 0. Okay, I worked it out. If we again look at FSMerc as the 2 most significant bits set in the whole byte here, that's a decimal value of 192. And if you subtract from these numbers 192, you get 1, 2, 3, 4, 5, 6, 7. That's simple. You just have to think about it. I don't think anymore this is a data sheet, it's an intelligence test. Anyway, for this table, they didn't have a look at these 6 bits here, but at the whole byte, okay? So we are basically looking here, again, the 6-bit pattern in the field itself at these bit combinations from 501 to 000111. And here's the first page of that chapter 17 explaining all the diagnostic bits. And I won't read out everything here, I just will point out some highlights. So, the first 7 error conditions here, so bits D0 to D6 in our diagnostic message, will put the thing into failsafe mode. That is, it stops working until it's rebooted, either by us or by its internal watchdog. Please note, all these error conditions are hardware error conditions, ranging from a RAM error to an EEPROM error. However, if there is an EEPROM RAM cache error or an ADC block error, this doesn't put the chip into failsafe mode. These errors are just reported for some reason. Footnote 17. Here's footnote 17. Reporting is done through the bits E0 and E1 of the regular messages of the bits DX of the diagnostic details message. See table 10 for more details. So, these bits E1 and E0 are contained in the regular messages we've already implemented that return us actual magnetic measurement data from our chip. And here's table 10. So the bit combination 0, 1 would indicate a diagnostic fail, and then we can send a diagnostic message over to the chip and get back the diagnostic message with the detailed information. For more about these regular messages, see the related video. Card here, link in the description. Anyway, footnote 17 basically applies to all other error conditions and bits with one notable exception, and that would be the BZ sensitivity monitor, which is disabled by default. However, the datasheet doesn't state anywhere how you can enable that. 3 more oddities on that page. First, the bits D9 to D11 are not documented. What else is new? Second, here for temperature sensor monitoring, there's an error with that. It's reported and then the temperature value is set to EET35, which is never mentioned again anywhere in the datasheet, but I guess EE stands for a value written in the EEPROM somewhere, which represents a temperature of 35 degrees, but that's just my guess. And finally, third, the footnote 18 for the BZ, BX and BY sensitivity monitor failures. That footnote states that these diagnostics are disabled when you run the chip at 3.3 volts. So they only work if you run it at 5 volts. Why? Bits D18 to D20 are documented on the next page. 2 oddities again. First, the diagnostic item supply voltage monitor and regulator monitor is disabled by default, and no information is given anywhere in the datasheet how you can enable that. Again. Also, again, footnote 18 so applies to that item, meaning it only works if you run the thing at 5 volt, not 3.3 volts. The rest of the diagnostic items on that page are not reported in the diagnostic message. Let's go over the related code, and we start with the first private section in my class definition. There I added the MISO opcode for diagnostic to the enum class MISO opcode, and of course also to the array with the MISO opcodes. Finally, I added that meso opcode to the enum class received. And by the way, we are now in the public part of the class. The 21 diagnostic bits within the meso message are modeled by the enum diag items, unsigned integer 32. And I choose to just use an enum and not an enum class, so you can use binary operations on that stuff here without the need to cast back and forth. And I didn't model the 3 undocumented bits D9 to D11. The 2 bits in the meso message, the FS_merc, or as I guessed, failsafe mode entry root cause, are modeled by an enum class again, failsafe cause, unsigned integer 8. And here they are from none, built-in self-test, digital diagnostic, and that error interruptions thing. The alternative meaning of the bits in the 6-bit field diag count, so our analog diagnostic counter, in case the failsafe cause was an error interruption, are modeled in the enum class failsafe error, unsigned integer 8. And here are the 7 error interruptions documented in the datasheet. Plus, I added here a none, all 0, just in case when I have to return such a value and we do not have as a failsafe cause an error. I have a new method, Boolean send diagnostic, which of course sends the diagnostic MOSI message. And I have 4 new methods to retrieve the data from a receive diagnostics meso message. The first being last diagnostic diag items, which returns you all those 21 diagnostic bits in the form of a diag items enum. Of course, several bits can be set in here. Then I have last diagnostic diag items, which gets as an argument a diag items, so a combination of bits, and if one of these bits is delivered back, then this method will return true, otherwise it will return false. So you can basically use that to test specific bits. Last diagnostic failsafe cause returns you, of course, the failsafe cause. And last diagnostic failsafe error returns you the failsafe error. That is the error interruption. That's it for the public part, and we are now entering the second private section of the class definition. There I have added 2 more bit masks. One for the 2 most significant bits in that byte that contains that FS_merc field, and one for the 6 least significant bits in that byte that contain that analog diagnostics counter. I also extended the typedef union meso message by adding a struct diagnostic. So the first 3 bytes in that message were all those diagnostic bits. And the 4th byte in that message contained in the 2 most significant bits that FS_merc, and in the 6 least significant bits the diag_count. And we are already in the CPP file looking at the implementation of send diagnostic, which is of course very simple. We're just sending an empty MOSI message, so we just initialize our MOSI message here with the marker other and the MOSI opcode diagnostic. We send the message and we return. Last diagnostic diag items, which should return us all the diagnostic bits, is a bit of a bit-banging affair. Remember, diagnostic bits within the diagnostic struct is an array of 3 bytes, meaning diagnostic bits itself is a pointer to that first byte. And I cast that pointer to be a pointer to a 32-bit integer. And then I take the content of that 32-bit integer. That is, I'm reading 1 byte more than there really is. And I mask out the additional bytes and the bytes not used by the diagnostic bits by binary ending that with a bit mask, and then I return that. No cast necessary because diag items is just an enum and not an enum class. Last diagnostic diag items, which tests for specific bits that have been returned in the message, works exactly the same. So I create here my 32-bit bit array, and then I binary AND that with the items, the bits I want to test for, and if that is not 0, then I return true. Otherwise, of course, false. Last diagnostic failsafe course works like so many of these methods before. I just take the field fsmerg diag count in the diagnostic struct in my meso message, and I binary AND that with the bit mask for fsmerg and cast that to be an enum class failsafe course, and I return that. Last diagnostic failsafe error has to handle an exception. First, I test here if the last diagnostic failsafe cause was actually a failsafe cause error. Otherwise, I return failsafe error none. You remember that was that special 0 value in the failsafe class error in case we don't have an error. Otherwise, I do the usual. I take the field fsmerg diag count within the diagnostic struct, binary AND that with the bit mask for diag count, cast that to an enum failsafe error, and I return that. And here's a sketch to test the whole shebang. And I switched on the lights. Yes. So, in the setup, I threw everything out but for the serial stuff at the beginning, the SPI begin, and the begin of our class, with the error handling included, of course. In the loop, I do now a send diagnostic, followed by the usual serial print MLX90363 last, and a delay of 500 milliseconds. And I extended that serial print MLX90363 last function to print out received diagnostic meso messages. So first of all, here I'm printing out all the diagnostic bits using the last diagnostic diag items testing for a certain bit. Then I print out the diagnostic failsafe cause using the last diagnostic failsafe cause method in a switch statement. That is followed by printing out the diagnostic error interrupt or interruption, again using last diagnostic failsafe error inside a switch statement, and finally I print out the diagnostic loop counter using last diagnostic loop counter. And here's the result on the serial monitor. So after I pressed start, the first message we receive is of course a knob. That's just the leftover from the begin. But then the next message is actually the diagnostic items. That is all the bits. And they are all 0. Great. That's what we expect. But for D18, field magnitude too low. And of course the field magnitude is too low because I haven't have any magnet near my thing here. Let me activate the auto scroll, and we see now also here jumping around the value of the loop counter. It's mostly 0. That's a disappointment. Let me switch out to scroll off and scroll up again. It's all 0.
0, 0, 0, 0. Interesting. 0. Oh.
Here we get another value. 41. 42. 41. 41. Oh, there was a 40. 39. So that loop counter is doing something, but to be honest, I can't tell you really what. Anyway, we were talking about D18 field magnitude too low being here remarked as an error bit, and we don't have a magnet here. Let me scroll again. And now we put a magnet here, and nothing changes. Let me try something. Let's close the serial monitor and restart it. That should reset our chip and do a reboot here. And now, this is to keep that on the screen, I put my magnet somewhere here and my mouse is moving. And we start. And now that bit is gone. So obviously, this test is only done at startup time, at power up, or if you reboot. Let me remove the magnet and see if the bit comes back on. No, it doesn't. Maybe if we send a request for some magnetic data to the chip, it will do that test again. Hopefully. But that's something for another day. Anyway, that portion of the code obviously works so far. And you see the loop counter, it's now producing some random numbers. That leaves us with the last 4 MOSI, respectively meso messages, oscillator counter start and oscillator counter stop. Hexadecimal opcode 18 and 19, respectively 1A and 1B. These messages enable you to evaluate the slave's internal oscillator frequency. The sequence of these messages is almost self-explanatory. So, in a first SPI transaction, the master sends over an oscillator counter start and gets as a reply, at least here in figure 16, a challenge echo, probably a knob challenge echo. It's never stated explicitly anywhere, but this also implies that the SPI transaction before was the master sending a knob message to the slave. Anyway, after a defined time t oscillator counter, the master sends an oscillator counter stop message to the slave, and the slave replies with an oscillator counter start. Yeah, it has another name here again, like in the other table. Who cares by this point? Finally, the master can send over any message and gets back the oscillator counter stop meso message from the slave, which finally contains an oscillator counter. Figure 17 shows you a timing diagram of the whole sequence. And here T oscillator counter is defined as the time between the rising edge of the slave select line after the first SPI transaction and the rising edge of the slave select line after the second SPI transaction. Quite hard to implement in Arduino land, but anyway. And T oscillator counter should be between 500 and 30,000 microseconds. Please note that the MISO message sent back from the slave during the first SPI transaction is denoted X here, so any message, not NOP challenge echo like in the table above. Also, the MOSI message we need to send over to the slave in the third SPI transaction is here also denoted as X, like in the diagram above. However, if you have a look at table 22, which we analyzed in depth when implementing our reboot sequence, card here, link in the description, it says after you send a MOSI message oscillator counter stop, you are only allowed to send as a next MOSI message a NOP. Yeah. Anyway, with the counter value received in the last SPI transaction, you can now calculate the internal oscillator frequency using this formula. How precise that calculation is depends on how precise you could time that T oscillator counter thing. And you cannot make that very precise in an Arduino environment. And here are the 4 messages. So, oscillator counter start MOSI and oscillator counter start MISO, as well as oscillator counter stop MOSI messages, are all empty messages. The oscillator counter stop MISO message contains here in bytes 2 and 3 a 15-bit counter value. Let's go over the code real quick. It's the same old. So in the first private section of my class, I've added the 2 new MISO opcodes here to my enum class MISO opcode as well as to my array MISO opcodes. Moving on to the public part of the library, I added the same MISO opcodes here to my enum class received. Then we have, of course, 2 new send methods here, send oscillator counter start and a send oscillator counter stop, as well as a new last function, oscillator counter stop counter, which returns us the counter value inside the last received oscillator counter stop MISO message. And we are already in the second private section of the class, where I added a bit mask counter value for masking that 15-bit counter value inside the MISO message. And the 2 new MOSI opcodes inside the enum class MOSI opcode. I also extended the union MISO message by adding the struct oscillator counter stop that contains the counter value in that MISO message in the bytes 2 and 3. Please remember, the counter value is only 15 least significant bits of these 2 bytes or that 16-bit word. Therefore, I needed that bit mask that we defined above. We're already in the CPP file again, and the implementations of the send oscillator counter start and send oscillator counter stop methods are basically the same. Initialize a local MOSI message and send it. The only difference is that here in the initialization I pass the MOSI opcode oscillator counter start and here oscillator counter stop. The method last oscillator counter stop counter just takes the counter value inside the struct oscillator counter stop inside the last MISO message union and binary ends that with that bit mask counter value, so we only get the 15 least significant bits. Now for the sketch. I extended the serial print MLX90363 last function to also print out a received oscillator counter start as well as oscillator counter stop message. The oscillator counter stop also prints out the last oscillator counter stop counter value. I didn't make any changes to the setup, but of course we have a new loop here. First I print out that we are starting the oscillator, then I send an oscillator counter start and print out the last received meso message. Please remember, this will be the first time we enter the loop a knob. That's a leftover from our begin inside the setup. Then, if the last received meso message was an oscillator counter stop, I print out the calculated frequency of that internal counter using the formula given in the datasheet. Then I wait for 25 milliseconds. Remember, the oscillator counter can be between 500 microseconds and 30,000 microseconds. That is 30 milliseconds. Then I print out oscillator stop and I send oscillator counter stop, and again I print out the last received meso message, which should be the acknowledgement for our send oscillator counter start, that is oscillator counter start meso message. And then I wait 500 milliseconds and I repeat. Please note, I didn't answer any knobs here. I'm going really aggressive, even if the datasheet states, at least in one chapter, that you should send a knob after an oscillator counter stop. We'll see how that works out. Here we go. Let me press enter. And let's stop the auto scroll and have a look. Okay, so oscillator start, and then we get a knob message as expected. Oscillator stop, nothing happens. We do an oscillator counter start again. Okay, and we get our first counter stop counter result. And if we apply the formula for that, that gives us about 19 point something megahertz, and in the next round it's 18.55 megahertz, and from there on it's quite stable, 18.55 megahertz. Let me activate auto scroll again. Yeah, so not quite 19, but as I said, the timing, to implement the timing between both rising edges of the oscillator counter start and oscillator counter stop MOSI messages, a bit tricky in the Arduino environment, but if you want, you could do better. But anyway, what that also proves is that the datasheet is not only inconsistent in places regarding the naming and incomplete in places, many places, but it's also contradicting itself, writing one thing in one chapter and stating another in another chapter. That's really not fun. But I'm happy that the code is working. That's it for today. We kinda reached a milestone, that is, we really implemented all MOSI and all meso messages that this chip supports. That said, I will probably tweak a little bit more on that library when I have an idea. There are some things I really don't like. For example, in the class definition, that first short private section, that has to go somehow. And there's a lot of stuff to optimize, like the timings I'm using inside the library are now fixed for 3.3 volts. We could change that to 5 volts and so on. However, I will take a little break now from this series because I have a repair coming up. And after that repair, we will probably repair in 2 videos, teardown analysis and then the actual repair. And then after that, we will continue with our mighty, but at least in regards to the datasheet, very annoying MLX90363. and we will explore all the configuration options and what they can do for us when we really want to measure magnetic fields. Till then, bye!